Hi guys, so to continue chapter 4, which is quantum in 3D for your quantum 2 class, we're looking at finding simultaneous eigenstates for our angular momentum, the square of our angular momentum, and one of the components of our angular momentum. So what we're going to do to approach this problem is that we're going to use a ladder operator technique. So our ladder operator technique is similar to the one we've already used. So we're going to introduce an operator that's either going to go up or go down, so increase or decrease our angular momentum. And we're going to define it as being Lx plus or minus I Ly. So we're defining that. And then we're looking at the commutator of this with Lz. So if we're looking at the commutator with Lz, we're looking at what is the difference when you apply one and then the other. So with Lz, we see that we can break our ladder operator into Lx. And again, it's either plus or minus. So I'm kind of condensing two equations into one line here. And then we've got I Ly. So again, we've already done this work, and we know that Lz commutated with Lx gives us I bar Ly. That is the difference when you apply them in a different order. And then plus or minus, we're going to pull that I out, and we introduce another negative I bar Lx. So that negative I comes because we apply z and then y instead of y and then z. So that switches the sign. Okay, so our commutator with Lz looks like a plus or minus h bar Lx. So that's actually our second term above, plus or minus I Ly. And that is our commutator of Lz with either our raising or our lowering operator there. Okay, so we can rewrite that even a little further as, because it's Lx plus or minus I Ly, see that's above here, that our commutator of Lz with our raising or lowering ladder operator ends up being plus or minus h bar times our raising or lowering ladder operator. So we're going to put that equation in our back pocket and come back to it. Similarly, you can look at what the square of your angular momentum does when applied in different orders with our raising and lowering ladder operator. And you'll see that you get a 0, so that the square of your angular momentum commutes with our raising and lowering ladder operator. Okay, so moving right along with this. If we've got f as an eigenfunction of L squared and Lz, our angular momentum squared and one of our components, then we're going to make the assertion that so is our ladder operator, raising or lowering, applied to that function. It would also be an eigenfunction of these two things. So our equation that says that these two items commute also says that these two items commute, right? So remember, these L's are operators. They're doing some sort of operation on that function f, but it doesn't matter which one we apply first. This statement says that there is no difference in the order that we apply them. If that's the case, we can substitute in, on one hand, if f is an eigenfunction of our angular momentum squared, we should get an eigenvalue times the eigenfunction. And we should be able to apply that in either direction so that we still get that same eigenvalue. We still get that same eigenvalue, even applied to this as our eigenfunction. So same eigenvalue, new eigenfunction. So that lets us know that if that our ladder operator applied to our function is still an eigenfunction of our momentum squared, and it's an eigenfunction with the same eigenvalue. So we had the eigenvalue lambda of f. Okay, what else can we say? Well, we can say that that other equation we boxed that said that LZ and our ladder operator don't commute, that we're going to have this extra factor if we apply them in a different order. That lets us know that if we apply LZ to our ladder operator acting on an eigenfunction, and we try to switch the order, that we are going to get this extra component of either plus or minus h bar times our ladder function. And let's say that LZ has this eigenvalue mu with this eigenfunction f. That lets us know that we're going to get a new eigenvalue when we apply a ladder operator to our eigenfunction. Okay, let's write that out. So what that lets us know is that our ladder function applied to our eigenfunction is still an eigenfunction of this component of our angular momentum. But this is a eigenfunction with a new eigenvalue. And that new eigenvalue is going to be our old eigenvalue plus or minus h bar. So our raising operator raises the eigenvalue of this component by a factor, or not a factor, h bar, and our lowering operator lowers it by h bar. Now, there's a caveat right here, right? We know that we can't exceed our total angular momentum with just the z component. So there's a top rung of our ladder operator, just like there was before. So our top rung, we're going to say, has the eigenfunction ft for the top. And that if you try to apply the raising operator once more, you're going to get a 0. Now there's some information in a footnote about this if you want to look into this a little harder. So we're going to introduce an h bar times L as the eigenvalue of this component at our so-called top rung of our ladder. So that means that Lz acting on this eigenfunction that is our top eigenfunction is going to give us this eigenvalue, and again our top rung eigenfunction. But we're still going to have, remember, it doesn't matter how many times we apply the raising and lowering operator to our L squared, we're still going to have the same eigenvalue for that guy. Now, because when we apply a raising and then a lowering, or a lowering then a raising operator, we're going to see this kind of operation happen. Let's just write out the equation and then talk. So we're going to see that we can simplify this operation in this way. So I'm just writing out right there a raising operator and then a lowering operator, or a lowering then a raising, and I'm condensing this all down into one equation with the stacked pluses and minuses. We end up with L squared minus LZ squared minus or plus I times I again times H bar LZ. And that is from all the definitions I have boxed before about what is our angular momentum squared, what are our commutation relationships between, say, Lx and Ly here in the parentheses in that second line there. So if we take this and we rearrange, we're going to rearrange to give ourselves that the angular momentum squared can be written as raising and then lowering, or lowering and then raising, plus our z component squared minus or plus h bar times our z component. Get my laptop to behave. So we're going to have this top rung operator that we can instead write in this way. So I've got plus, minus, minus, plus. You know what? I'm actually going to simplify my life and just look at one of these at a time. So I'm going to look at do this. I'm going to look at just that lower set of pluses and minuses, right? So if we apply a lowering or a raising operator, then a lowering operator, the raising operator applied to ft is going to give us a 0, right? So that is coming from, we're saying this applies first when we distribute that function into all these operators. And so we get a 0 there. Then we've got LZ squared applied to FT. So we apply that twice, we just get our eigenvalue for our LZ twice. And then we've got H bar LZ applied to FT. So we're going to get an H bar and then our eigenvalue again, which is H bar L. So all of those things are our eigenvalues that have to do with those operators above. That leads me to my angular momentum squared operating on my top rung eigen function, giving h bar squared L times L plus 1 on Ft. So what does that say? Well, that says that the eigenvalue that shouldn't be changing at all of my angular momentum squared must be this. It must be h bar squared L plus 1. That is our eigenvalue of our angular momentum squared. And it is in terms of our maximum eigenvalue of this one component of our angular momentum. So that's a good place to pause. I'm going to say there's also a bottom rung. And the bottom rung will use the function f for bottom, where we apply our momentum or not our momentum operator, our lowering operator to that bottom rung, and we get a 0. So we'll pick up there with the next one.